I'm Ennan Zhai. Today I'm going to talk about independence as a service. This is a joint work with Richard Chen, David Wolosky, and Brian Ford. Today's cloud services rely on redundancy to ensure the reliability. For example, Amazon S3 replicates each data object across multiple racks. For another example, as a famous application-level cloud service, iCloud runs EC2 and Azure for redundancy. Unfortunately, seemingly independent redundant systems may share deep and hidden dependencies. Such unexpected common dependencies may lead to correlated failures, undermining the redundancy efforts. In practice, cloud service outage caused big losses. As shown in this report, downtime in one data center can cost about $500,000 per incident. Let me show one simple example about correlated failures. Assume I'm a service provider and I'm maintaining 3 individual racks. I replicated the important status of my service across the 3 racks. I hope this redundancy configuration can enhance the reliability of my service. Unfortunately, unbeknownst to me, the 3 racks depend on the same aggregation switch. If this aggregation switch fails, the 3 racks will become unavailable at the same time. This simple example illustrates documented failures. 2 years ago, correlated failures resulting from EBS happened in Amazon. In Amazon, EBS offers storage support to EC2 service. There are many physical machines running in EC2. Some application providers, such as Netflix, rent redundant virtual machines running on those physical machines to ensure the reliability. In the EBS layer, each EBS server offers storage support to multiple EC2 physical machines. In this Amazon outage event, a glitch happened in one EBS server. This single point failure led to correlated failures across a lot of physical machines, making redundant virtual machines running on those physical machines become unavailable. Even worse, it would become more challenging to handle the correlated failures across redundant cloud providers. A lightning damaged the power source supporting Microsoft and Amazon services in Dublin 4 years ago. The damaged power source led to correlated failures across a lot of cloud providers. Applications redundantly using those cloud providers become unavailable at the same time, despite the redundancy efforts. Assume an application is using 2 cloud providers for redundancy. So the cloud providers depend on some third-party infrastructure components, such as ISP routers, power source. If the lightning damaged this power source, the 2 cloud providers will become unavailable at the same time. So this case is more challenging to handle because cloud providers don't usually share information about the dependencies. There have been a lot of existing efforts trying to address the correlated failure problem, such as diagnosis system, fault-tolerant systems. However, all of them try to address the problem after the service outage occurs, which has been demonstrated not effective to complex cloud environment. So in this paper, we aim to prevent unexpected correlated failures before the service outage occurs. Our intuition is to evaluate the independence of redundancy configuration. We propose independence as a service. So our system can tell you which alternative redundancy configuration is the most independent before your service adoption. In general, a service provider Alice can use INDaaS to evaluate the independence of any redundancy configuration. In a typical redundancy configuration, there are multiple data sources. Each data source is responsible to hold one data copy. For example, in Amazon S3, data sources are different servers or clusters. For iCloud example, data sources can be different cloud providers, such as EC2 and Azure. Let me show you one typical workflow that Alice uses INDaaS to evaluate the independence of a given redundancy configuration with 2 data sources. In the first step, Alice submits a specification to INDaaS. Then, INDaaS automatically collects the dependency data from each data source. Next, INDaaS produces dependency representation based on the collected data and evaluates the independence of the target redundancy configuration. So now, Alice can understand the independence score of the target redundancy configuration. Before her service adoption, she can run our system to all the alternative redundancy configurations and understand which alternative redundancy configuration is the most independent. Then she can use that one for her service. However, if data sources are from different cloud providers, our current solution doesn't work. This is because no cloud provider is willing to share the dependency data with our system or other cloud provider. So, INDaaS also offers a privacy-preserving approach to help each data source to privately calculate the independence. Each data source can calculate the independence and only send the independence score back to INDaaS without leaking any information. In this case, each cloud provider cannot know any information, and our system only knows the independence score. So it forwards the independence score to Alice. Building such a system is actually non-trivial in practice. We need to overcome some technical challenges. The first challenge is how to automatically collect the dependency data. The second challenge is how we produce dependency representation using the collected data. The third challenge is with the dependency representation in hand, how we efficiently audit it. The final challenge is how we privately evaluate the independence if a data source doesn't want to share any information. So in this talk, I will show you the solutions to the 4 challenges, respectively. Let me use this architecture as the roadmap of my talk. The first challenge is dependency acquisitions. In general, we reuse existing data collection systems already in the current cloud providers to automatically collect dependency data. We only transfer the output of those collection systems into our defined format for the following process. Due to limited time, I skipped this part, so please see our paper for more details. Now, after the dependency data collection, we need to produce the dependency representation using the collected data. Our solution basically is a fault graph. The fault graph could be looked at as a combination of DEX and logic gates. Let me show you details. We assume we already got the dependency data of this example redundancy configuration. In this example redundancy configuration, we have 2 data sources, server 1 and server 2. The dependency data includes different types: software, hardware, and networking. Now, let me show you how we produce a fault graph representing this example redundancy configuration from top to bottom. In the first step, we need to produce the root node of the fault graph. So the fault graph should be the redundancy configuration failure event, because we are trying to represent a redundancy configuration. Next, we use AND gate to connect 2 data sources, server 1 and server 2. AND gate means all the sublayer nodes fail. The upper layer node fails. Actually, this is the intuition behind any redundancy effort. Next, we use OR gate to connect different types of dependencies underlying each server node. OR gate means one of the upper layer node, underlying node fails, the upper layer node will fail. So next, we use OR gate to connect different hardware dependencies underlying each server node. We use AND gate to connect redundant networking paths. Finally, we use OR gate to connect different software components running on each server. So far, we have already produced a fault graph representing our example redundancy configuration. Then, with the dependency representation in hand, let me show you how we efficiently audit this representation. Generally, we have 2 algorithms balancing the cost and accuracy. The first algorithm is a minimal foresight algorithm. We borrow this algorithm from other area. However, the complexity is NP hard, so we will not use it. We propose an efficient failure sampling algorithm. Let me introduce failure sampling algorithm. So failure sampling algorithm is a heuristic algorithm, and it contains many sampling rounds. In each sampling round, we flip a coin to assign 1 or 0 to each leave node in the given fault graph. 1 means failure. After the assignment, we need to check whether the root node of the given fault graph is 1 or 0, namely failure or not. We also need to maintain a list recording fault sets. If the root node fails, we produce a fault set including all the leave nodes whose values are 1. Let me illustrate failure sampling algorithm using this example. So in the first sampling run, we flip a coin to assign 1 or 0 to each leave node. We assume we got this result, and server 1 and server 2 hardware fails, but switch 1 works. In this case, the root node fails. So we include a fault set. In the fault set, you can see we include server 1 and server 2 hardware failures. We enter the next sampling round. In the second sampling round, we flip a coin again to each leave node. We assume we got this result. In this case, the root node doesn't fail, so we skip this sampling round, and we enter the next sampling round. In the third sampling round, we repeat flip a coin to assign 1 or 0 to each leave node, and we got this result. This time, redundancy configuration fails again. So we record the corresponding fault set, namely switch 1 fails, and we enter the next sampling round. After a lot of sampling rounds, we got a list recording to all the fault sets. We can rank these fault sets according to their sizes. Because the smaller size, more dangerous the fault size should be. Of course, if we can get some other information, such as failure probabilities, we can rank the fault sites according to the failure probabilities. After get the ranking list, so we can calculate the independence. And our system offers different equations to calculate the independence. For example, summation of the sizes of the fault sets and other more smart equations. So far, I already presented the basic workflow of INDaaS. In the case data sources are from different cloud providers, we need to calculate the independence privately. Let me show you how we solve this problem. This is a more specific scenario where a service provider, Alice, wants to select several cloud providers for her redundancy configuration. Each cloud provider depends on some third-party infrastructure components. Of course, this information is sensitive, so no cloud provider is willing to share it. And for Alice, she wants to select 2 cloud providers for redundancy, but she doesn't know which 2 are the most independent. So she asks our system agent, A and B, or B and C, or A and C. If we can directly deploy our system on a trusted third party, we actually directly solve the problem. However, in practice, cloud providers are reluctant to share such information. We definitely can use a secure multi-party computation to address our problem. Unfortunately, SMPC is very hard to scale in practice, so we already had the results evaluating this. Let me show you how we solve the problem. In the first step, Alice submits a specification to INDaaS agent. In this case, the agent wants to evaluate the independence based on the similarity between dependency data sets maintained by cloud providers. So the agent sends a dependency collection request to each cloud provider. Each cloud provider generates a local data set according to the data collection system. Each cloud provider should compute Jacquard similarity between its dataset and the other cloud provider's dataset, and use Jacquard similarity as the independence of each alternative redundancy configuration. Jacquard similarity is very simple. We only need to know set intersection cardinality and set union cardinality. Let me show you how we use Jacquard similarity to calculate the independence. For example, if we want to compute the independence of the redundancy configuration, including cloud A and B should compute the set intersection cardinality and set union cardinality. Then they can calculate the Jakarta similarity. So in this example, the Jakarta similarity is 0.5. This is the independence. In the INDaaS agent side, the agent should maintain a table to record the independence of each alternative redundancy configuration. So the similarity between B and C is 0.25. Again, the similarity between A and C is 0. So we like 0 because 0 means fully independent. Now, the agent ranks alternative redundancy configurations according to their similarities. Then got the ranking list and send the ranking list back to Alice. So Alice can understand which alternative redundancy configuration is the most independent. So our current goal is to privately calculate the Jakarta similarity. Fortunately, there has been existing protocol which can privately calculate the set intersection cardinality and union cardinality. The protocol is named PSOP. PSOP allows K parties to calculate set intersection cardinality and union cardinality without leaking any information. For example, in this scenario, we assume there are 3 parties and each of them maintains a local dataset. After running PSOP protocol, each of them will know there is only one overlapping element and what is the set union cardinality, but they cannot know any other information. So let me show you how PSOP protocol works. In the initial phase, each party has a commutative encryption key. Commutative encryption, in principle, has an important property. For a given message M, if multiple parties encrypt the message, regardless the order, we will have the same ciphertext. All the parties construct a circle, and each party encrypts the item in local dataset maintained by them, and sends the encrypted dataset to the successor party. The successor party does the same thing and sends the next party in the circle. So until each party obtains its original dataset, which has been encrypted by all the parties, they publish the encrypted dataset. Because of the commutative encryption key property, each party can compare the ciphertext and learn how many elements is the overlapping one. And in this example, they can know there is only one overlapping element, and they can know the set union cardinality is 7. So let me show you how a system uses a PSOP protocol. And we repeat the previous operations, submission, specification submission, and send the request to each cloud provider. So cloud provider perform the PSOP protocol and without leaking any information, and we got the Jakarta similarity, and the agent record this number. So B and C also perform the PSOP protocol, and we can get the similarity and record it. So now the agent remove all the Jakarta similarity from the table and send the ranking list back to Alice. So Alice can understand which alternative redundancy configuration is the most independent. So far, I already presented all the basic solutions to our challenges and the evaluation section. So we have 3 parts of evaluation. The first part is realistic case studies. So we deploy our system on Yale Campus service, and we evaluated the practicality of our system using some real case studies. So please see our paper for more details. And now, let me show you the evaluation about the 2 algorithms trade-off. We evaluated the efficiency and the accuracy trade-off of the 2 algorithms. We use factory model as the dataset of our evaluation, and we produce different scales of the topologies. So let me show the result about the largest set. In this evaluation, we run failure sampling algorithm with different sampling runs to this topology, and we obtain this result. So we can observe failure sampling algorithm with 1 million sampling runs can find out many important 4 sets, and only needs about 200 minutes. So the final part is to evaluate the overhead of PSOP protocol. To compare with the PSOP protocol, we also implemented another well-known private set operation protocol named Kissner and Song, and we evaluated the network and computational overhead of the 2 protocols. And this is the network overhead evaluation. So due to limited time, I need to skip this part, and so you can see our paper for more details. In conclusion, INDaaS is a first step towards the reliable cloud. Yeah, we solved 4 technical challenges, and we evaluated our system with realistic case studies and large-scale simulations. So you can find out some more information from our website, and we will be at the poster session tonight. So thank you very much. And any questions?
Mark Lillibridge from HP Labs. So what exactly do the cloud providers not want to know about their stuff? Because it sure as heck looks like they can figure out what each other is doing.
You mean the... So actually, you mean that if application providers wants to select a different cloud provider's case or the first case?
No, I'm saying that if Amazon wants to know what Microsoft's infrastructure looks like, it can use your protocol to figure out what they're doing in common.
Our protocol actually can preserve this privacy thing. So actually, in your example, the Amazon company cannot know any information of a Microsoft company.
But you give me the cardinality of the intersection, so I keep giving subsets of my stuff until I figure out what you have and don't have.
So because in our protocol, actually, we only calculate the similarity, right? And during the protocol, each party cannot know any, element, because they cannot know the specific element in the whole protocol. So they cannot know the information underlying each cloud company.
I'll take it offline, but basically by changing what I say I have, I can look at the cardinality and figure out what they've got in common.
Okay, cool.
Downtown Columbia. So how do you consider the probability of each individual component that it fails? For example, it may be more likely that an ISP fails rather than a lightning strikes somewhere.
So your question is about the failure probability?
Yeah.
Oh, so I think in practice, the failure probability is very hard to collect in practice. And I remember there is a paper to successfully get the failure probability. So actually, in our system, we directly use the, if the cloud provider can offer the failure probability to us, and we can directly use the failure probability to calculate the independence or rank the full sets. But our system doesn't focus on how to collect the failure probability from a real cloud.
Chris Kozirek, Stanford University. Great work. I want to follow up on the same topic. Can you tell us a little bit, if I care about fail probability, if I care about my service having 4 nines on some fit rate, can I use your tool to basically say, find me the way to deploy my service that has this fail probability? So I want the goal, and I don't want how to deploy it. Can your work help with that in some way?
So you mean how to deploy our system in a given cloud provider?
Yes, I know I can use a bunch of services within or across clouds, and I want to get 4 nines or 5 nines. Okay, can you figure out how to deploy this? Is there something, some way I can use your tool for that?
Yeah, so this is a tricky question. So actually, I can answer your question from this way. So our target goal is actually generate the ranking list. So if you are the cloud administrator and you are maintaining the for example the Amazon service, so the target is to show a ranking list to you, and you can select the most independent redundancy configuration from this ranking list. Actually, we just use the score to rank all the alternative redundancy configuration. This is our target.
Thanks.
Pramod from MPI SWS. So it seems that while computing this independence scores for across cloud, you don't make use of fault graph. You compute the private index score just on the sets. Any reason for doing that?
Can you say it again?
So I was wondering, like, you don't make use of fault graph when computing private score across cloud providers. So can you do it, or can you make use of fault graph also when computing this?
So you mean whether we can use the fault graph to handle the privacy preserving case, right?
Yeah.
I think we cannot, because a cloud provider doesn't want to share the information, right? But I can imagine this thing from this way. If you can find out a trusted third party or trusted auditor, and maybe the auditor can collect the dependency data from each cloud provider, and that guy can build a fault graph to to represent all the cloud providers structure and run our failure, for example, failure sampling algorithm on this topology and get the result. But I don't think in practice we can use the fault graph to handle the multiple cloud providers case.
I guess you're going to lose some.
I should let these people have a question because they were actually in the queue for a while. So one last question for the break.
Quick clarification. Can you go back to the slide with the commutative encryption?
You mean the working process of a PSOP?
Yeah, this one. No, this one is the one I was referring to. This one with the encryption. So when you say publish, are you publishing this only to the independent agent, or are you publishing it to each other?
Publish all the encrypted data set.
But to everybody, or just the independent
Everybody.
agent?
Yeah, because every guy in this scenario can see, the published encrypted data set, because all the data sets, 3 data sets have been encrypted by all the parties. So we don't need to worry about they can, extract any specification, a specific element from this encrypted data sets, right? So all the guys should publish it, and we can compare how many overlapping pieces of a ciphertext between them.
But you're saying that the ciphertext is equivalent because of the commutativity.
Right. Yeah, exactly. So that's the property of the commutative encryption.
So if I'm KD and I see KF has also published some same value that I have published, then I know that he has the same dependency. Is that correct?
Right. Yes.
Thank you.